this is James, and welcome to episode 2 of this differential geometry series. For this episode, we start with definition 2.1. A tangent vector, written v sub p, to R3 consists of 2 points of R3, its vector part v, and its point of application p. In the figure below, we illustrate one way to visualize these tangent vectors. We have 2 points, P and Q, which we use as points of application, and then we have 2 other points, V and W, which we use as vector parts for 2 tangent vectors. The first tangent vector is V sub P, which starts at the point P, and then it continues in the direction of V for the length of V. Then we have the tangent vector W sub Q, emanating from the point Q in the direction of W for the length of W. And we will refer to V sub P and W sub Q as our tangent vectors in general. Next, we introduce the tangent space. So, given a point P of R3, the set T sub P of R3, consisting of all tangent vectors that have P as a point of application, is called the tangent space of R3 at P. Here we just imagine taking the standard Euclidean three-dimensional axes and relocating them to the point P and calling that our tangent space. Next, we have a simple definition. A vector field, V, on R3 is a function that assigns to each point P of R3 a tangent vector, V of P, to R3 at P. So, to break that down, a vector field, V, takes a point P and assigns it a tangent vector. We denote that tangent vector V of P. Next, we define the natural frame field. Let U1, U2, and U3 be the vector fields on R3, such that U1 of P is the tangent vector 1, 0, 0 applied to the point P, and then so on similarly for U2 and U3 evaluated at P. And these are defined as such for each point P of R3. We call U1, U2, and U3 collectively the natural frame field on R3. Now we consider the following lemma. Lemma 2.5 states, if V is a vector field on R3, there are 3 uniquely determined real-valued functions, V1, V2, and V3, on R3 such that V, the vector field, is equal to the linear combination of vector fields V1, U1 plus V2, U2 plus V3, U3. The functions V1, V2, and V3 will be called the Euclidean coordinate functions of V. All right, now let's briefly prove that these real-valued functions V1, V2, and V3 exist. We will simply write the tangent vector V of P in coordinates, and we'll call the coordinates V1 of P, V2 of P, and V3 of P. We know that each of these will depend on only P, since the tangent vector V of P only depends on what the point P. So that is how V1, V2, and V3 are introduced. We then just check that the equation linear combination that we were stated in the lemma actually gives us equality to the vector field v. Writing v of p as these components, v1 of p, v2 of p, and v3 of p, we use the definition of vector addition, tangent vector addition, and say whatever the value of v1 of p is, we use that as a real value multiplied by the tangent vector 1, 0, 0 applied to the point p, and etc. for v2 and v3. Then we use the definition of the natural frame field to replace the tangent vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 with our u1, u2, and u3 vector fields. Then the vector field v and the vector field v1, u1 plus v2, u2 plus v3, u3 will always return the same value at every point p in R3.